Hey everyone, welcome back. Today's video is equations of motion. Now, we have been talking about equations of motion or sort of dancing around them for weeks now. Go back, remember we talked about sum of forces and sum of moments, right? We said that the sum of forces on some body, we'll call it A. This is going to be dt of linear momentum of A. And we said that the sum of moments on A about A, this is equal to ddt of h, A about A. Now, with exam number 2 behind us, we have effectively talked about all parts of these equations. I'm going to expand Newton's second law. This is going to be let's say ma va dot. Now, we are also making the assumption in these that the mass and therefore the inertia are going to be constant. We're not looking at burn rates here. Now, in order to finally put all of this stuff together, what do we need? We need to be able to do 3 things. We need to be able to define the effort in the problem, so sum of forces and moments. We need to be able to talk about momentum terms. So make sure that you're comfortable with mass, inertia, parallel axis theorem, etc. And then you have to be able to define the kinematics. So we need to be able to make some claim about the linear acceleration of centers of masses. And I'll go ahead and expand Euler's. This is I omega dot plus omega cross I omega. So of course you need to be able to define the inertia and then the angular accelerations. Now, if we were able to write these equations, what's the point of doing that? Imagine that you have some body in front of you and you're able to write these expressions and you put it all together, all of the specifics for the problems. In these equations, what are the unknowns? Well, we're going to assume that you're able to solve for forces and moments. So I'm going to write known underneath. Known, or you solve for it, or it's specified, or it's created by some engine or motor, etc. The mass and inertia terms, we're going to say that these are going to be known, and the speeds are going to be known. All that's going to leave, right? We can see that the only thing left are going to be VA dot and omega dot. These are our unknowns, which really means the unknowns inside of omega dot and VA dot. The unknowns are really things like Q double dots and theta double dots. So the point of equations of motion, at least at the level we're looking at it right now this semester, the point of the equations of motion is when you take all of your information about the problem and you put it together, and then you're able to solve for some kind of unknown Q double dot or theta double dot. Now, if you were able to solve for Q double dot or theta double dot, what's the point then? We've talked about this in lecture, but just remember that if you're able to solve, let's say for a Q double dot, and you can integrate this Q double dot with respect to time, that's going to give you Q dot. And specifically, it's going to give you Q dot as a function of time. If you can solve for the Q double dot at this moment, Q double dot is this, at another moment it's something else. What you will get is a time history of the speed of the object or the problem or whatever it is, whatever quantity you're looking at. You numerically integrate acceleration, you will get velocity. Now, what happens when you numerically integrate a second time? That means you're now going to get Q as a function of time. What this process is telling us is that if we take the equations of motion, we solve for unknown accelerations, we perform on these calculated values, if we perform some kind of numerical integration, that is, if we integrate these numerically, we can find some kind of time history of this thing, and we're going to do this In the next video, I'm going to show you how to do this process using a command in MATLAB called ODE45. You don't have to do it in MATLAB. You could write C code or Python, or you can do your integration anything you want. We're just going to use ODE45 because it's built in. Okay, so this is a nice little introduction. I'm going to clean this up, and let's talk about the specific problem that we're going to do today. The problem we want to do is a very simple one. This is the first time we're doing equations of motion. Let's say that there's a person, and this person has, they have a ball in their hand, and they're going to throw this ball. So there's the ball, right? They're just giving it some initial velocity, and off the ball goes. Now, intuitively, right, from our experience, we understand that this ball is going to have some kind of ballistic trajectory. It's going to be parabolic. It's not going to be perfect because there's air friction, right, in the air. But gravity is going to cause this to accelerate down, which means it's going to hit some kind of maximum value, and then it's going to return to Earth. Okay, here's what we want. We want the equations of motion for that object, for the ball that the person is throwing, which means we need to go through all of the setup necessary to write this expression and put in all of the known quantities for it. We want to go all the way down to the end and solve for the unknowns. Now, do we need, so this was Newton's second law, do we also need Euler's second law in this specific problem? Well, it depends on what we're doing with the ball. Consider that there are all kinds of interesting effects that can come from rotations of objects. Think of golf balls, for example. You can get a golf ball to turn based off of how you spin the ball. So the question then is, are we concerned about the spin of this ball? For this example, let's say no. Let's say that in this example, not only are we not worried about it, but I'll put this comment in the corner. I'm going to write a comment that says we are modeling the ball as a particle. All right, I'm just going to put it in a box up in the corner, right? Put this claim somewhere on there so the grader knows what you're doing. We're modeling the ball as a particle. That means that there is no frame attached to the ball itself. We don't care how the ball is spinning, and we're not going to worry about Euler's second law. I assure you we're going to have to do it in later problems. Today, let's just keep it easy. Let's just do a point mass, right? It's all the mass is at one point and no spin. So we need to go through and be able to call out these quantities. Well, not the DDT. We know that this is going to be MA VA dot. Okay, so we just have to build all these terms. Very simple problem. Don't overthink it. Let's start with the kinematics. We know that VA dot is ddt of VA, which means it is the second derivative with respect to time of P in A. Okay, so we just got to find P and A and take two derivatives. Here's the diagram for the problem. Let's sort out what P and A is doing. Are there any constraints in this problem? Is there anything grounding this ball? Is there a string? No, nothing, right? This ball is basically, it's effectively in free fall, right? If I took this pin and I just chucked the pin, right? Nothing is constraining this ball. So if we put point in somewhere, we can put it here, that's fine. You can put it in the guy's hand, you can put it on his foot, whatever you want. Let's call the ball A. We need to track the position of A. Well, okay. Clearly the A can go left and right, and A can go up and down, and we're gonna do this problem in MATLAB later. So let's also add a depth to it. Let's just go ahead and give body a full three-dimensional position vector. So I'm going to say it's Q1 in the xn, and it's Q2 in the yn, and it's Q3 in the zn. Okay. At this point, I think we're all okay taking derivatives, especially something very simple like this. You take the derivative twice, and we're going to get double dot x hat in, and we're going to get q2 double dot y hat in, and we're going to get q3 double dot z hat in. Okay. Jot that down in your notes. That takes care of that one. What do we need to do about mass? Well, again, we're not changing mass. This isn't a mass variant system. So we can come down and we can just write a comment, and we can just say that MA is known. And if we want to, we could also say MA is known and constant. Okay, so it's just a number. Understand, when we get to the coding part of this, I am just going to plug in a number for the mass, and if we want to change the mass, we just change that number in the code, and all the math takes care of it. So we got VA, we got MA. There are those are done. Jot these down in your notes. Let's do the sum of forces and moments. Now, this system, there's only the one body, body A. We need to do a free body diagram of it. This is almost a free body diagram. Free body diagram is just going to be this, right? Separated from the rest of the diagram, and then we have to annotate it. Now, clearly there's gravity acting on this, so MAG. Let's go ahead and let's talk about putting friction on this. When we run the code for it, we're going to do it with and without friction, just so we can see how it compares. But let's say that we want to put some kind of drag, a viscous drag on this ball. Now, I put a video up talking about viscous friction models, Stokes' law, other models dealing with drag coefficients. Let's use this definition. Let's say that FD equals negative, excuse me, negative CD A mu A, and then let's do U squared. Okay. And if you go back and you look at that video, you'll see I talk a bit about how to implement this and also what each of these terms are. As for implementing this in code, we're going to use something like this. We're going to put these terms all together, CD, A, mu, and these will all become some damping coefficient. Usually, I tend to call this term, I tend to use a beta for this term, but again, you can call it whatever you want. And then we're going to take U, and we're going to divide by the magnitude of U. This is going to give us a unit vector, magnitude of 1. And then in order to capture this magnitude portion of U squared, we can do a dot product. So we can do U dot U. Now the U dot U is going to be scalar. And again, that's the magnitude associated with this. U divided by magnitude of U, this is going to normalize and give us a unit vector. So this is going to capture the direction. Clearly, if the ball is going this way, then the drag is pointing in the other direction. So the U over magnitude U, unit vector, negative will reverse the direction, and then this will carry the magnitude. Okay, we have this, and we have this. So tell you what, I don't want to rewrite this one over over again as we go through the problem. So jot this down in your notes. And moving forward, I'm just going to leave it as FD, knowing that we have a definition for FD, right? We can always go back and put it in, which we will. So we've got that taken care of. We have free body diagram. What should we do next? Well, next we just need to write an equation for sum of forces. Now, we know the direction of MAG. We know that this is minus MAG in the y hat in direction, and I'm going to say plus FD. I'm not going to put a vector, an axis or a frame or anything on it, because we know that inside of this declaration there is the U divided by magnitude U term, right? And that's going to take care of this. It's going to have a direction inherent in its definition. So you could always, that thing that we wrote down, you could take that, you put it in here. Okay, So this was the setup for the problem, right? Like the mass was obvious, the VA dot is obvious, and the forces are very easy. So we've taken care of this. All right, which means we can take all of this and we can put it all together, right? We can come up with one big equation. So I'm going to clean this up. We're going to put all of this math together, and then we're going to talk about how to solve it. We're putting the equations of motion together. We've defined all three of these parts. Let's start with some of forces. We said it was minus MAG in the y hat n, and then plus FD. Remember, FD has that has the frames inherent, right, inside of it. This is equal to MA multiplied by Q1 double dot X hat n plus Q2 double dot Y hat n plus Q3 double dot Z hat n. Okay, this is the equation of motion. Now, how do we know that we're done with the problem? Well, we wrote the general expression for Newton's second law, and then we've gone back and we've replaced everything with the specifics. And that does include FD. Notice that I wrote this as FD, but remember, we have a definition for FD, so we're free to go back and insert that in. If you just write FD, you are not done. You have to define what FD is. And again, we're going to get lots of practice doing equations of motion, especially on multi-body systems, mechanisms. So, what do we do with this now that we have this? Well, what we can do is we can actually break this into a whole series of equations. Right now, if I point you to this equation and I ask you, what kind of equation is this? When I say what kind of equation, right, we could say it's trigonometric or polynomial or logarithmic, something like that. Because these are dots, right? Because these are dots, this is inherently a differential equation. Right, because these dots right here, remember that the dot is the second derivative with respect to time. So since the derivative is contained within the expression itself, within the equation, this is a differential equation. Next, what is the order of this differential equation? Order, question mark. Now, when I say order, you have to know what to look for. When we're talking specifically about differential equations and the word order comes up, what that means is look at the derivative term. So look at the dots, for example, and then ask yourself, what is the highest order dot term? In this equation, we have double dots, right? You could have an equation with one dot or triple dots or quadruple dots, etc. Now, this order, what it's talking about is it's asking what is the highest order derivative term. Now, you might be inclined to answer this with a 2 because there's 2 dots. I'm going to say that's you're on the right path. That is not the correct answer. The correct answer for this equation is actually 6. And here's why it's 6. It's Q1 double dot and Q2 and Q3. And notice that each one of these are in different directions, right? One's in X, one's in Y, one's in Z. We could, if we want to, and we're going to in a moment, we could take this equation, we could break it actually into 3 different equations. We could break it into equations for X, and equations for Y, and equations for Z. So this one equation is vector, and it's acting in 3 different directions. So we could actually take this and break it into 3 different equations. Each one of those equations would have an acceleration term. We'd have a Q1 double dot, a Q2 double dot, a Q3 double dot. And when you do that, you're going to have 3 second order equations, which makes the whole system 6 total. When we talk about the order of an equation, you have to take those things into account. Okay, so let's do that. Let's take this equation and let's just rewrite it in 3 parts. Let's say MA q1 double dot is equal to, so notice I'm dropping the x hat n term, right? So I'm going to take this equation, right now it's vector, I'm going to rewrite it as 3 scalar equations. So the scalar equation for the x hat n direction. On the right hand side, the only thing in x hat n is this term. There is no gravity in the x hat n direction, and that's going to leave fd, and I'm just going to write it as fd dot xn, the xn component, right? Because again, this fd has some vector terms in it. Next, ma q2 double dot. So this is here's the y hat n term, and tell you what, I just realized something. Since we're dealing with a 3D problem, let's put the gravity in the z direction. There we go, quick fix. We haven't gone too far in, so I think this is okay. So ma q2 double dot, this was the y hat n. We put gravity in the z, so all that's going to leave is fd dot y hat n. And then let's write the last one now, ma q3 double dot equals, and we are going to have gravity here. We'll have minus mag plus, and this is fd dot zn. All right. Okay, so again, all we did is we took the vector equation and we wrote it as scalar equations. Good. Here's what we're going to do next. I'm going to clean this up a little bit, and we're going to take now these 3 equations and we're going to rewrite them using what are called state variables. Okay, state variables. Now, the purpose of putting things into state variables is you take a system of, you have your original vector differential equation. We wrote that as a system of second order differential equations, right? There are 1, 2, 3 second order differential equations. Each one of these is second order because, again, look at the double dot. And what we're going to do using state variables, we're going to rewrite the system as 6 first order differential equations. Okay, right now they're 3 second order. We're going to rewrite them as 6 first order. Why do we want to do this? What's the point in taking this system and rewriting it in this form with state variables? If we do this, this is going to be the form that we can put directly into numerical integration. So if we want to use ODE 45 in MATLAB, it needs to be written as a series of first order differential equations. So we're going to take these, we're going to rewrite them, and then we're going to put them into code. Okay, let me clean this up and we'll get started. Whenever you think of state variables, what it means is you're going to go through this equation and you're going to replace any of these, anything that changes with respect to time, right? You look at the derivatives. So we have q1 double dot, q2 double dot, q3 double dot. That means we're going to replace the q's, because they're the ones with the dots. We're going to replace them with x's. Okay, by default, we tend to use x as state variables, regardless of what field you're in or what problem you're solving. It could be a physics problem or a fluids problem or chemistry problem, it doesn't matter. Okay? The standard for state variables is an x. Now, how many state variables do we need? A moment ago, I told you that this system, this equation was 6th order, right? This is a 6th order differential equation. Now, the fact that it's 6th order, it tells me that we need 6 state variables. And those state variables are going to be x1 through x6. All right, that's how we're going to start with this. You look at your equation, you figure out the order of the system, you figure out how many state variables you need. Okay. Next, let's write down what the state variables are. So we said there's 6 of them. So we've got x1, x2, x3. I'm going to do a little separator between them. just to keep it organized. And then there's x4, x5, x6. You'll see why I did this in a moment. So what are all of these state variables? Well, again, look at where the derivative is. We've got q1 and q2 and q3. Let's make those our original state variables. So x1 is q1, and x2 is q2, and x3 is q3. Next, what then are x4, x5, and x6? Well, notice we need to build up to q double dot, right? This is q double dot, and right now it's just q. So let's make the next three state variables the derivatives of those first three. So q1 dot, q2 dot, q3 dot. Okay. Now, if those are the state variables, what we're going to do next is we're going to define the derivatives of the state variables. So this was, if we call this vector, if we call this whole vector x, right? The vector x contains x1 through x6. What we want is we now want to define x dot. So how about x1 dot, x2 dot, x3 dot, and x4 dot, x5 dot, x6 dot. All right. And again, same vector, right? X1 through 6, and here's x1 through 6. Now we've just put dots on it. So what are these? Well, the first three are q1, q2, q3. If we take the derivative of those, that makes this q1 dot and q2 dot, q3 dot. What do we do with the next three? Well, we take the derivative of these, right? Notice that these were already the derivatives. This was q1 dot through q3 dot, and that's x4. When you dot x4, it's the second derivative. So q1 double dot, q2 double dot, and q3 double dot. All right, so what is this vector? Well, if this vector was x, then this vector is x dot. Okay. Now, what can we do with this vector? Well, this that we have right here, notice that these are actually differential equations. They're inherently differential equations because it's x1 dot, x5 dot, right? So, can we take these expressions for the x dots, and can we write them in terms of the x's such that we could then numerically integrate these six state variables, these six x dots? Okay, that's the claim, that if we can integrate these six, we can actually solve the problem. So what we're going to do is we're going to take these six and we're going to rewrite them in such a way that q has been eliminated. Let's see if we can write them purely in terms of 1, 2, 3, 4, 5, 6 x's. Okay. So we'll work example. x1 dot is q1 dot. Okay. I can come back to this column and I can say that q1 dot is x4. We can say that q2 dot is x5. q3 dot is x6. Okay. Next, what's going to happen with these three? Well, now we need a solution for q1 double dot and q2 double dot, q3 double dot. Where does that come from? Well, it comes from the equation of motion, right? We have this original differential equation, right? And it's currently vector, but we rewrote it a minute ago in scalars, right? Where we solved for MA q1 double dot and MA q2 double dot, right? And now all I'm saying is that I need to write those same expressions solving for the q1 double dots. Okay. If we want to solve for q1 double dot, what's going to happen? Clearly we need to divide by the mass. So I'm going to say 1 over ma. And then it's whatever forces were left, right? And we saw that there is no gravity in the x hat n, and there was only the drag term left. So this is going to be fd dot x hat n. What's going to happen on x5 dot when we go to solve for q2 double dot? Well, same thing, right? Like we could take this equation and we look at just the y hat n terms, and we will get 1 over ma fd dot yn. And then of course the last one, you take the third of those scalar equations and you solve for, I'll get you in 1 second, honey. You take the q3 double dots, solve those, you get 1 over ma, and then it's minus mag plus fd dot zn. All right, we've got a couple of comments left on the theoretical side of this one. Let me clean all this up and take care of a cat, and we'll come back and we'll talk about the last couple of theoretical steps. I've rewritten the last 3 of the first order differential equations. Remember, there's still the first 3, right? The x1, x2, x3. And those are part of that system of state variables as well. But let's just focus on these last 3 for a moment. Now, these are differential equations. We would like to solve these differential equations. If we do solve them, they're going to be able, we're then able to make claims about time. We can answer questions like, how fast is the rocket going after a certain amount of time? Or where is the rocket after a certain amount of time? Something like that. How would we go about solving these differential equations? Well, this FD term it's fairly complicated, right? Minus CD a mu, that's the easy part, that's just a number. And then U divided by magnitude, U, is going to be a direction, and then we have this dot product, U dot U. Now, if there is some nice and convenient way to analytically integrate this, that would be wonderful, right? If you could analytically integrate it. Friction models tend to get fairly complicated when one body is connected to another body, right? When you have kinematic chains, right? Multi-body systems, these equations get incredibly complex. And even with something relatively small like this, it makes the analytical integration incredibly difficult, if not impossible. So if you're in a situation where you cannot analytically solve the differential equations, that's when you numerically integrate them. And to be honest, most real-world systems are going to be something complicated that you cannot analytically integrate, so you then numerically do it. So we're going to do that in the next video. What if we simplified this? Let us simplify this just a bit, and let's talk about the analytical solutions to problems like this. So instead of doing something very complicated with the friction, what if for now we pretended that friction was 0? If we just took it out, what happens to these? Then clearly x4 dot is equal to 0. x5 dot is equal to 0, x6 dot is going to equal minus g, right? Because the MAs are going to cancel, and then you're just going to be left with the acceleration negative gravity. Well, if these are the solutions, then that makes it really simple, right? So doing something as small as setting aside friction allows us to analyze the system analytically. Now, this was the Q1 double dot, this was Q2 double dot, and that was Q3 double dot. Okay. Suppose that we numerically, analytically integrate these. So if I want Q1 dot, that means I'm going to integrate Q1 double dot dt, and hey, right now, without friction, it turns out that Q1 double dot is 0. So what do we get when we integrate 0? Do we get 0? Is Q1 dot 0? Not necessarily. This says that the acceleration is 0, which means the change in velocity is 0. It doesn't necessarily mean that the velocity is 0. You can be driving your car at a constant velocity, right? And your acceleration is 0, but your velocity is non-zero. So what happens when you integrate, remember that there's integration constants. So we will end up with an integration constant C1, which is when you go through all that math, what it will do is it will come out to be, I'm going to say comma 0. Sure. This is the initial value of Q1 dot. And then Q2 dot, we're going to integrate Q2 double dot, and same story, right? There's going to be, this is 0, but there is some constant of integration, which when you dig into that, you will find this is the initial condition. Okay, which makes sense, right? If there is no velocity, then how fast you're going at a certain moment in time is equal to how fast you've always been going, right? How fast you're going in this direction. Well, you've always been going that fast. There is no acceleration. What happens with Q3 dots? Well, we want to integrate these, so I'm just going to bring negative g over negative g dt, and what we will get is we will get negative g times t, and then plus that integration constant, Q3 naught dot. Okay, we can do this. This isn't too bad. What happens when we integrate these again? Well, we have speeds. Remember that we want position. So if I take these equations, and I'm just going to do them on this side, we want Q1, and I'll specify this one. We want Q1 as a function of time. Okay, what are we going to do to get Q1? Well, we're just going to integrate this. So I'm going to integrate the Q1 dot expression, which was this one. We have Q1 dot sub naught dt, and here we're going to get Q1 dot sub naught multiplied by time, and then plus, and remember there's always the integration constant. So what is the integration constant now? Well, last time it was the initial speed. This time it's the initial position. So this is Q1 sub naught. Notice it's not Q1 dot, right? This is an equation for position, and we get the initial position. So your position at some moment in time is equal to where you started plus how fast you're going multiplied by time. If we want to solve for Q2 as a function of time, we're going to, similarly, we're going to integrate this, and we're going to get Q2 dot naught plus t, times t plus Q2 sub naught. Same equation, right? Basically same equation. What about Q3? So Q3 is a function of time. We're going to integrate this expression. So we're going to integrate minus gt plus Q3 sub naught, and then I'll put a little dt in the corner. Q. Okay, that's fine. We can integrate this. Q3 as a function of time is equal to, when you integrate the negative gt, and remember we're integrating it with respect to time, we will get negative negative 1/2 gt squared plus the second term, so plus Q3 dot sub naught multiplied by time. And remember, as with the previous cases, there is an integration constant, and that is going to be the initial position. So Q3 sub naught. Okay, you've probably seen equations like this before. 1/2 gt squared. If you look at, or if you Google kinematic equations for bodies in free fall, you'll get some equation that says distance is 1/2 gt squared, okay? That's where these equations come from, these kinematic equations. We took the equations of motion, we made some simplifications, we took friction out, for example, and then we analytically solved the differential equations. Now, how useful are these? Well, they'll give you a ballpark estimate, right? But obviously these kinematics, they have no friction in them, which means, depending on the situation, limited usefulness. If you're simulating a skydiver and you don't put friction in the model, then that skydiver never actually hits terminal velocity and they continue to accelerate. So some situations, these approaches are no good at all. Okay. So I think that's good for this problem. Here's what's going to happen next. I'm going to make another video that's going to screen capture MATLAB. And we're going to take all of this math, we're going to put it into MATLAB, and we're going to look at some plots. We're going to talk about how to actually set that integration up in ODE 45. And we'll look at some figures and we'll do some explanations there. The next couple of videos is going to be still equations of motion, and we're going to start looking at more complicated systems, things like pendulums and linkages. Now, in those systems, we are not going to go all the way through state variables, okay? In my undergrad dynamics class this semester, you actually do not have to use state variables on any homework or exam problem. I did this discussion because you are going to have to use state variables in later classes, maybe classes you're taking right now, and this might be helpful, and especially coupled with the next video for ODE 45. Okay, so I think that's good. I'll see you next time. Yeah. Take care of yourself. I'll see you around.